Fingerprints are the most infallible means of identification. They are the most important individual evidence which a forensic scientist finds at the scene of crime. When a criminal touches different surfaces at the scene of crime, he leaves behind a sweat residue which is colorless. It is called latent fingerprint. Latent means hidden. But it has to be developed. And for developing it, we have to use one or more reagents. These reagents either get physically tagged to the components of sweat or they chemically react with it. Under the first category, we have mainly the powders. The colored powders become attached to one or more component of the sweat residue and impart color and render the latent fingerprint visible. Under the second category, we have reagents like ninhydrin which react with amino acid components of sweat and impart color to it. Ruthenium tetroxide is also one of the chemical reagents which reacts with the oily components of sweat. Oily components are mainly the organic compounds in the sweat, the amino acids, the proteins, hydrocarbons, carbonyl compounds, and so on. They constitute almost 0.5% of latent fingerprint. Ruthenium tetroxide is a very strong oxidizing agent. The oxidation state of ruthenium is +8, something very unique, something very high. It's not very stable. And the moment it reacts with organic constituents of sweat, it is reduced to ruthenium dioxide, where the oxidation state is 4 and much more stable. Ruthenium tetroxide is thus converted into ruthenium dioxide, and ruthenium dioxide is black in color. It gets deposited along the ridges. So, in a way, ruthenium tetroxide first reacts with the organic components of sweat. It gets reduced to a more stable form, ruthenium dioxide, which is black in color, and that black color becomes adsorbed on the ridges and renders visibility to it. The advantage of this technique is that on light colored surfaces, very sharp fingerprints develop of black color. They are easily visible. One may not use even a lens to render visibility to them. They are very clear. The disadvantage is that ruthenium tetroxide is a highly reactive as well as an unstable compound. Although it's an inorganic compound, it is a liquid because it is largely covalent. It has to be dissolved in some organic solvent, and organic solvents are explosives, some of them are inflammable also. So, the technique requires very careful handling. Moreover, there are many surfaces which themselves react with ruthenium tetroxide. As I said, it's a very reactive compound. You have to take care while handling it. But yes, if appropriate handling is done and carefully the method is carried out, very sharp black colored fingerprints are obtained, and they are obtained on a wide variety of surfaces. The only condition is that the surface should be inert to ruthenium tetroxide. It itself should not react with ruthenium tetroxide. Moreover, ruthenium tetroxide has to be prepared largely before taking the fingerprints. It's not very stable. There are some problems in preserving it also. But on the whole, it's a versatile technique. It's a technique which once the fingerprints are developed, they are very sharp, they are very clear, and you do not need any further light source to enhance them. They themselves are quite sharp and clear.
Dear students, after studying this module, you shall be able to know the characteristics of ruthenium tetroxide reagent. You will learn different methods of applying ruthenium tetroxide to crime scene evidence. You will also come to know about the mechanism by which ruthenium tetroxide detects fingerprints, and lastly, after learning this chapter, you will come to know about an assessment of ruthenium tetroxide technique of fingerprint development. So let us start with the introduction. Forensic identification specialists are often faced with substrates that are difficult to process for friction-rich impressions. Since friction-rich impressions are both unique and persistent, they are invaluable form of identification. However, they are not always in a readily useful form. Crime scene investigators, fingerprint examiners, and other forensic identification practitioners are often tasked to locate, develop, and preserve these latent impressions on a wide variety of tools and techniques have been developed to accomplish this objective. Sequential processing of impression-bearing evidence involves using different methods of fingerprint development that act upon the different components of friction skin residue. If one technique fails to develop one type of residue, then other method may act on a different component and obtain the desired result. Ruthenium tetroxide, also referred to as ruthenium 8 oxide or RuO4, is a volatile and unstable liquid at normal temperatures and atmospheric pressure. It is a versatile reagent for detecting latent fingerprints on a host of crime scene evidence. It uses as a fingerprint reagent emanates from its tendency to oxidize the oily components of fingertip sweat. In this reaction, ruthenium tetroxide itself is reduced to relatively stable ruthenium dioxide. Ruthenium dioxide, which settles on the ridges as black or black-gray deposition. The dark-colored prints persist over prolonged periods of time. Now let us see preparation and properties of ruthenium tetroxide. Ruthenium tetroxide is prepared by the oxidation of ruthenium 3 chloride RuCl3 with sodium periodate, which is NaIO4. The chemical reaction is depicted in the given figure, which states that 8 RuCl3 plus 5 NaIO4 plus 12 H2O gives out 8 RuO4 plus 5 NaI plus 24 HCl. The reagent is isolated as a golden yellow sublimable solid with pungent odor. It has a melting point of 25.4 degrees Celsius and a boiling point of 40 degrees Celsius. Its density is 3.29 gram centimeter per cube. It possesses a tetrahedral structure as shown in the given figure. Ruthenium tetroxide is toxic and explosive in nature. When heated above 100 degrees Celsius, it decomposes explosively into ruthenium dioxide and oxygen. The reaction is shown in the given figure. It is therefore pertinent that the reagent must be handled in a well-ventilated fume cupboard using gloves and goggles. Ruthenium tetroxide may explode even at room temperature if brought in contact with organic solvents like alcohol or ether. Its solution may, however, be prepared safely in carbon tetrachloride, in which it is freely soluble. Its solubility in water is meager. A saturated aqueous solution at room temperature has a concentration of 2%. Now let us have a look on the mechanism. Ruthenium tetroxide is an aggressive oxidant. It oxidizes virtually every hydrocarbon. It also oxidizes compounds of carbonyl classification. It cleaves the double bonds of unsaturated organic derivatives. It is this later reaction which paves the way for detection of latent fingerprints by ruthenium tetroxide. The reagent attacks the double bonds of unsaturated fatty acids present in fingerprint residue and yields an intermediate ruthenate ester. This intermediate is unstable and spontaneously decomposes into hydrate ruthenium 4 oxide. RuO2NH2O, the later oxide of ruthenium, is quite stable and imparts black color to the finger ridges. Taking oleic acid as a representative unsaturated fatty acid in fingerprint residue, the mechanism of oxidation by ruthenium tetroxide is set out in the given figure. Now, dear students, let us discuss the methodology. For the purpose of detecting fingerprints, ruthenium tetroxide may be applied to the crime scene evidence in several ways. One method is to prepare a solution of the reagent in water and treat the sample by dipping, spraying or swabbing. However, has been stated earlier, the solubility of ruthenium tetroxide in water is quite low, as a result of which the aqueous solution of the reagent takes a considerably long time to develop the finger marks. In order to speed up the development process, an alternate route may be adopted. Rather than applying the reagent in solution state, the crystals of ruthenium tetroxide may be sublimed by heating in a water bath and the vapors so generated be impinged on the evidence. However, this technique too has a shortcoming. If the heating is too rapid or if the temperature goes beyond 50 degrees Celsius, ruthenium tetroxide is likely to decompose explosively into ruthenium dioxide and oxygen. A better method is to dissolve ruthenium tetroxide in a halogenated organic solvent and vaporize the yellow colored solution at low pressures. The fumes are directed on the crime scene evidence. An assembly for generating vapor of ruthenium tetroxide dissolved in a halogenated solvent is shown in the given figure. As stated earlier, ruthenium tetroxide is freely soluble in carbon tetrachloride. However, tetra-decafluorohexane, 1-methoxy-nonafluorobutane, and 2,3-dihydrodecafluoropentane have proved to be better solvents as far as detection of fingerprints is concerned. Their structures are depicted in given figure. Carbon tetrachloride, also known as by many other names, the most notable being tetrachloromethane, also recognized by the IUPAC carbon tet in the cleaning industry, is an organic compound with the chemical formula CC14. It was formerly widely used in fire extinguishers as a precursor to refrigerants and as a cleaning agent. It is a colorless liquid with a sweet smell that can be detected at low levels. Perfluorohexane or tetra-decafluorohexane is a fluorocarbon. It is a derivative of hexane in which all of the hydrogen atoms are replaced by fluorine atom. It is used in one formulation of the electronic cooling liquid insulator fluoroinert for low temperature applications due to its low boiling point of 56 degrees Celsius and freezing point of -90 degrees Celsius. It is odorless and colorless. Unlike typical hydrocarbons, the structure features a helical carbon backbone. Yet another method of applying the reagent to the evidence is to synthesize it during the surface treatment itself. Ruthenium tetroxide vapors are produced by mixing equal volumes of a 0.1% aqueous solution of ruthenium 3-chloride with a 11.3% aqueous solution of ammonium cerium nitrate. The reaction, which is set out in the given figure, is conducted in a closed chamber in which the evidence to be processed is suspended. The surface is exposed to the vapors of 20 to 60 minutes, whereby black colored fingerprints develop. Now, dear students, let us see the assessment of ruthenium tetroxide method. Ruthenium tetroxide reagent has the potential to develop fingerprints on porous surfaces such as ordinary paper, thermal paper, clothes, wood, on non-porous surfaces such as metals, glass, and on semi-porous surfaces such as adhesive tapes, vinyl tapes. A sample fingerprint developed by ruthenium tetroxide on paper is shown in the given figure. In addition, it can detect fingerprints on stones, walls, and wallpapers. It also works on greasy metallic items, cartridges, and coins. Since the reagent fixes the insoluble fatty acid component of fingertip sweat, it is possible to extend the methodology to all the aforementioned surfaces even when these are wet. Above all, ruthenium tetroxide can develop fingerprints on human skin, which is shown in the given figure. It gives better results on dead bodies than on live skin. The developed prints are stable over long periods. The ridges, which are visualized in black or black-gray hue, produce a sharp contrast against a light colored background. If the background itself happens to be dark, the developed prints may be lifted and transferred onto a white substrate. If the method fails to give positive results, the ninhydrin or 1,8-diisoflurane 9,1, which is also known as DFO method, may still be tried out on the same article. Now, dear students, let us summarize this chapter. In this chapter, we have learned that since friction ridge impressions are both unique and persistent, they are an invaluable form of identification. Sequential processing of impressions bearing evidence involves using different methods of fingerprint development that act upon the different components of friction skin residue. Then, in this chapter, we have learned that the ruthenium tetroxide method has broad spectrum applications as it can develop fingerprints on a very large number of crime scene evidence, including human skin. Apart from that, in this chapter, we have learned that the dark colored prints visualized by this reagent are clear, sharp, and persistent. However, the method is not very popular since the toxic and explosive nature of the reagent raises health and safety concerns. Then, after learning this chapter, we have come to know that it has a melting point of 25.4 degrees Celsius and a boiling point of 40 degrees Celsius. Ruthenium tetroxide is freely soluble in carbon tetrachloride and the solubility of ruthenium tetroxide in water is quite low. And lastly, after studying this chapter, we have come to know that ruthenium tetroxide reagent has the potential to develop fingerprints on porous surfaces such as ordinary paper, thermal paper, cloths, wood, non-porous surfaces such as metal, glass, and on semi-porous surfaces such as adhesive, tapes and vinyl tapes.